Hello everyone, welcome in this new destruction tutorial with Way. My name is Gabriel Neville, I'm a key FX artist and NPC film Montreal. During these last few years, I had the chance to do several destruction shots for films, commercials, and video games trailers. Therefore, I have a lot of interesting secrets and techniques that I'd like to share with you today. By the end of this course, you will be able to art direct RBD simulations, source debris, smoke, and even those additional electricity effects. Let's hop in. So let's start with the modeling of the road. So this is basically just a line. So I just draw a line and resample it to give it a bunch of points, and then I create the cross section. So basically the shape of the road. So how wide and how deep it's going to be. So 7 meters wide and 10 centimeters deep, and then I just sweep it. So it's going to extrude this cross section alongside the input line. I'm going to reverse it and UV transform it. This is for later. Cool. So we have our sidewalk. So it's basically going to take the same line, and it's going to this time not only do one cross, but like two cross lines. So over there, those two cross shapes are going to be extruded alongside the same line, and just then reverse it to put the normals in the right place. And then same thing, UV transform. This is for later. But yeah, that's it. And for the animation, it's basically just an animation from Xamo that I just scaled, offset it to fit the frame range, and then I just animated it on top with a transform to have this guy jump in the air into the ground. So nothing really fancy here. This is just the starting scene. And yeah, let's dive right in. And maybe last thing before we start, I can show you how to create this build I made up. So basically, I'm going to give it a bit more space to the network editor here. I'm going to split this by 2 by clicking on this little arrow over there. Split pan left to right. Same thing over there. And then I'm going to connect this network to this window to this one over there. By this, to do this, I'm going to click on this, click and select one. Same thing over there, and this one I'm going to select 2. So this one, that would just mean that those ones are connected and those ones are connected as well. So you can see that when I'm selecting something here, it's only changing on the left side. And the reason why I do this is because it's going to be pretty helpful when if I want to drag and drop some stuff around. But you'll see that later. And then also what I would like to do is add the geometry spreadsheet over there. So I'm going to click on this little arrow, split top bottom. And I'm going to click on the plus over there, new pen tab type, inspector geometry spreadsheet. I'm going to close the scene view, and I'm going just to put it down a bit so we can see a bit more of the viewport. So once you're happy with it, you can go and save current desktop as, and you can name it, and then it will be saved in your preferences. So for me, I'm just going to load my build, and then we're ready to go with Arnold. So we are going to use the shop network over there, and I'm going to create an Arnold channel network. I'm going to call it road. And I'm going to create a standard surface over there. One of the common issue you can have is that you're not going to see the textures on the viewport, and that's something that we can fix with a little trick that I'm going to show. So I'm going to put down an image node I'm going to go to $job, so like our folder, input texture road, and I'm going to select the albedo. All right, so that's cool. You can see like we're going to test it right now. The road, if I put the material on, you can see we don't see anything. So I'm going to select the shader, go to edit parameter interface, and I'm going to put a toggle over there and a file image. So for the toggle, I'm going to call it use diffuse. Same here. And here diffuse map. And same thing in the label. Cool. So now basically I need to put some custom thing so it gets recognized by the OpenGL. So here in the type name, I'm going to type OGL text 1. And the tag value, I'm going to put it to 1. And here on the toggle, I'm going to change the tag name to OGL use text and 1 on the tag value. Alright, so that's cool. I'm going to do this. And here basically I'm going to look for my file name over there, copy parameter and paste relative reference over there. And you can see as soon as I did that, now we have the textures in the viewport. Pretty cool, right? So wherever I change the texture, it's going to be in the viewport, even with an Arnold shader. So I'm going to put it back to the albedo. And then I'm going to select the roughness. I'm going to load it as sRGB linear. I'm going to put it in specular roughness. I'm going to keep it nice and clean. Then the normal. So for the normal, you need to type normal map. And also I'm going to put a bump 2D. And I'm going to take the displacement. And I'm going to basically combine the two. So the normal over there and the bump. I'm going to put the input here. The bump map is over there, the normal is over there. So I guess we can rearrange it a bit. And then the vector is going to be put in normal. That's pretty cool, all right. And basically we're going to do the same. So just create the same thing for the sidewalk and the cactus. All right, that's it. So we have the road and the sidewalk done, and we're going to test it right now. So I'm going to create an Arnold light, put it as a skydome, just like white for now. We have our render camera, and I'm going to go in the out context, and I'm going to create an Arnold node. Just to put the render camera over there, and yeah, we can render for now all the candid objects and with all the candid lights. Let's call it sky. The render view, it's going to generate the scene, then just basically it's going to create also all the TX files, so it's going to compute the textures in Arnold own format. That's cool. So we can see all the textures. The reason why we didn't see the textures on the character in the viewport was because we're using Udem. So to use Udem with Arnold, basically you need to put this Udem like inside the texture path at the instead of putting the 1001. You basically need to give the Udem data as a variable over there. So like the viewport won't recognize it, but Arnold will. So that's the most important. And to be honest, we don't really need the texture in the viewport for this guy. It was mainly for the road to get like some nice preview in the destruction. So now we know that what we're going to do, that we have the textures working, we have the shaders more or less done. So now I'm going to create a new geometry node, and I'm going to call it main rigid bodies. I'm going to dive right in, object merge, and I'm going to look for the road. Right, so we have the road over there. I'm going to create a material node, and I'm going to take this shader road, just so we can see it in the preview. That's cool. And so the first thing we want to do is basically define the area of what we want to destroy, because we don't want to destroy to fracture this whole road, because like otherwise it's going to be massive, and basically there will be like a really big amount of data that is pretty useless. So we're going to need to work pretty efficiency in like really define the area we want to work with. So a good thing for that would be to take a bit of room just under him and basically stop where the camera is stopping, so just over there. So I'm going to create a sphere, and I'm going to basically draw the area of work I want to use for my effect. So we can say we'll have something like this, a bit wider on the side. Can take a bit more, maybe a bit deep. So that's more or less the area we want to work with. So now I'm going to use a Boolean Fracture. Turn this sphere as a polygon. I'm going to increase quite a lot. I can use like 30 or something. And basically, so like if we try to put the geometry and the Boolean, something happened. We don't know why yet, but like I can see if I go to smooth wire shaded, we can see there's a line now. So if I put down an exploded view after that on the first input, we can see that we have this thing. We have this sphere just cut the part that we wanted. So that's cool, but I mean, like, that's not really natural in terms of look. So I'm going to switch back to the sphere that we had and put a mountain. So mountain will create some detail on the side first, so we just need to make sure we have enough resolution. So I'm going to increase it, and the mountain I'm going just to make sure that we have a good looking noise. We can try with the default for this case, and we can check if we have enough resolution on the side. It's a bit low rail still, so I mean we can turn this to 100. It's already a bit better. Let's try to 150. All right, so now I feel like we have some good resolution. What about the pattern? So the pattern that we have over there. I mean, it's all right. I would say it's all right. So let's skip this for now. Basically, the only thing now is you can see some weird stuff happening in the textures on the side. It's basically because we don't have any UV on the sphere, and we're not transferring. Basically, so how the Boolean works is going to create some inside surfaces. So those guys, I can put like an example. As you can see, those interior and exterior group. If I put like a color node, so after the exploded view, I just put select inside and I put it in red. And I'm going to use primitive. You can see basically all the inside surfaces are the new ones created, right, on both sides. So basically by creating some UV on the sphere and transferring it to the geometry, we'll have some UV on the inside. Because now, if I go there, zoom it a bit, so I'm just going to reduce the near clip. So that's why, you know, like sometimes when I try to zoom in, it just gets sad. It's basically the near clip that is too big. If I do a UV quick shade, you can see over there the UV are like getting a bit crazy, especially like here. So we're going to create some UV for the sphere. So the way to do it would be to just do UV texture over there. I'm going to copy this node, check the UV. So it's a bit weird, right? So we're going to use the polar one, because polar is basically the sphere initialization of the UVs. And then I'm going to use a UV flatten. And then you can see it's basically yeah, you can see it's not that deformed anymore, especially on the side, because we're going to use the side. So UV flatten, we should be good to go. All right, cool. So now let's just check the scale of the UV. So we can see here, we can see the checkerboard is like really big, and over there is pretty small. So either we do it before, but what I like to do is do it actually afterwards. So we can see here, we'll still have some weird stuff, and it's because we didn't really transfer the UV to the new geometry. So we need to click on copy cutting surface attributes, and in vertex attributes you need to call the UV. And so now we can see some stuff, but it's like it's really, really big. So I'm going to put a UV transform over there. I'm going to select the inside surfaces. And I'm going to copy the scale here on the two other ones, because like we want to uniformly scale those UV. And by just, so you can see like when we scale this up, now we can see the checkerboard like happening. So now the game would be to match more or less the scale of the UV on the inside from the outside. And now if I just look at the textures and go back to smooth shaded, you can see it's alright. It's doing its thing. So we should be happy with it. And then we can always, you know, like give also like another shaders on the inside surfaces. So we can say it's good enough in this case. So that's cool. I'm going to put a file cache, and in the file cache I'm going to save current frame, remove this $f, and actually I'm just going to rewrite everything. I'm going to create $job geo. I'm going to call the folder called fracturing, and $os slash $os.bgo.sc, which is the file format of Houdini. I'm going to click on this wheel here, and I'm going just to create an integer parameter for the versioning. So it's going to be just basically like a slider, which will allow us to switch between multiple versions. And I'm just going to put right here between those two guys. So if I do save to disk, basically we're going to see we have something called fracturing file cache 1 v0 file cache 1.bgo.sc. So the reason why it's called file cache 1 is because we're using $rs. If I middle click, you can have a preview of the full file path. So basically we might want to name it to like something a bit more relevant. In this case, I'm going to code road first fracturing. I'm going to save to disk, and then you can see road first fracturing. That's cool. I removed the $f because it's just like a one frame. We can see here we're not time dependent. We just want to bake this data for one frame. All right, we should be good to go. So now I'm going to split. And basically, I'm just going to split the working area with the non-working area. So if I go to the camera view, I'm going to select 9. I'm going to go to this wheel here, attribute name, and basically you can see I can select 2 pieces that were like automatically created. And in this case, I'm going to select the pieces we want to work with. And so the spot will be the active area. And this one, the non-active. Cool. All right, so that's nice. So now what we want to do is basically we're going to fracture this in multiple pieces. We're going to keep the same system. So like we're going to use Boolean mostly, but like we're going to generate also like cutting planes. So in order to do this, so I'm just going to put an attribute triangle here, put it to name, and I'm going to create a name attribute, and I'm going just to call it road active underscore, and it's just like I like to initialize with a kind of a clean name, because sometimes we can have several layers. So you can put in the same sim, you can put like the sidewalk, you can put something like this. And basically if I just keep the name I had, so I can go and switch to primitive piece 1, basically like when you're fracturing stuff on another layer, so like in sidewalk, we can have like a piece 1 as well. So like if everything is called piece 1, basically like the solver can have a hard time finding what's what, you know, like is it the piece 1 of the road, or is it the piece 1 of the sidewalk? So for now, as we only have like just one piece, I like to initialize with a good name, so just in this case road active. That's cool. All right, so now we're going to create those cutting planes that we're talking about. All right, so for the cutting planes, the standard approach would basically just to scatter some points on our geometry, create a grid, copy to points, attribute randomize the normal to get like different orientation, target point to copy to. So now we have like a bunch of cutting planes. You can go to inside sphere, increase a bit the size, maybe the amount a bit. And then just like use this as the Boolean over there. And have this. So like that's the standard approach. It can work well in some cases. So like if I put the mountain over there, basically here I'm just going to edit parameter interface, and I'm going to create a float and call it resolution. So this one's going to be copy parameter, multiply by the resolution, best relative reference, and this one copy base relative reference times resolution as well. So if I switch to smooth wire shaded, you can see now, like each time I make this bigger, I create new geometry, and also like if I just turn the resolution up, you can see like it's getting, we have like more polygons to play with, something a bit to get more detail. So now if I just use those guys, we should have a better pattern already, like in the cutting planes. All right, why not? So like that can be an option. See, like we have some nice, some good looking pieces over there, but sometimes we also have some a bit like crazy ones. For concrete, I prefer to do like another approach than this, to be honest, something that's a bit more predictable. Basically, I'm going to create some perpendicular cutting planes. So like basically the idea, so we have a bounding box of this object. We have one line that goes through the wideness of the object, and to the width of the object, we have the length of the object and the height of the object. So I have those three lines, and basically this line is going to copy orthogonal cutting planes, and we can basically just control more easily the amount and the shaping of our pieces. Don't get me wrong, this one is really good as well. It can work maybe for a little more organic look, but I'm going to go for another one. So basically the plan, we're going to create a bound, and yeah, just create 2 points, so a net there, and here I'm just going to create a null after the bound, and I'm just going to call it sample. So this one, a net. I'm going to create a spare input, drag and drop the sample node, and here in the point I'm just going to call it centroid -1 dy for the middle parameter. I'm going to create the one in the z. So same thing for the first one, we're going to put dx. That's all right. So now we're in the middle of the x-axis, in the middle of the y-axis. And just for the last one, basically, we're going to call bbox -1 d z min. That's cool. And now I'm going to duplicate this one and just put dz max instead. So now we have those 2 points. From 2 points we can make a line. That's pretty common, right? We put an add node, polygon, by group, bam, you have your line, right? And now if I put a resample over there, we can create an amount of points. Polyframe to create some nice normal. You can see like the normals are pointing along the line. And now if I copy to point a grid, so we're going to use the same grid as earlier, you know, with the one with the resolution stuff. Geometry copy to. Then I just need to change the orientation, the initial rotation, and you can see here, bam, we have our cutting planes. So that's cool. So now obviously it's like way too perfect in the orientation, but we can change it by randomize it. We're going to put n, and we're going to multiply side sphere add value, sorry. Yeah. And we can see here we're just like tweaking a bit the value just to break it up a bit. Code angle. So you can see we have like some stuff to play with. For now we can just like use the standard one. And if I just retake our Boolean Fracture sub, take the input geometry, put this as the cutting planes. Now if I put like an exploded view with a small value, you can see we have like a much more controllable shapes, and we can really like easily say, okay, we want like more on this side. We can control the noise and stuff like this. And so the exact same system can happen over there, but on the other side now. So instead of going to here bbox z in the z-axis, we're going to do this on the x-axis. So I'm going to copy here and put x min and use the centroid values for the z. And I'm just going to duplicate this and put x max instead. So you can see now we have this line, and we're just going to copy a bunch of grid. So now the thing is, our system is not entirely robust yet. And that's because you can see like it was working in this case because we didn't have a really wide stuff, but in this case it won't work because basically the input is like way wider than the input grid. So that means that we will need to change the size of the grid to have it like longer, right? So we can do it by hand in this case, just for now. And we can also like reduce the amount. maybe 5 and just increase to 60, something like this. Reduce a bit the randomness. You can put a merge over there. You can see now we have this kind of patterns that actually are pretty hard to get otherwise, because you know, like otherwise you would need to go with Voronoi fracturing and stuff like this, which can be a possibility, but like yeah, you wouldn't get that much size variation as well. And also, like if something is not just flat like this, it's pretty hard to get with just Voronoi and stuff like this. So for me, this is like a cool way for to get those kind of shapes for concrete. But now we can make basically this tool a bit more robust. So I'm not going to show it in this tutorial, but like maybe on another one I'll show you basically how I can make this HDA with you know, like the input lines Alright, so let's get back to it. So first thing, we might want to copy the UV transform we used, just to make sure that we have like a pretty uniform UV on the inside surfaces. And also that brings up another topic. Basically, we might want to isolate those inside surfaces with the new one that we're going to create with the cutting planes. So for that, basically what I like to do is, if I go on the Boolean Fracture, basically I just put a number on the amount of the number of the fracturing. So like here it's inside, we didn't put anything because it's the first one, but like then we just put inside 2, and that way on the explode view, so I just need to calculate a bit. All right. So we can like basically isolate the inside surface from the side and the one from the inside. You can see. So like this is the first one we did with the sphere to determine the area of work, and this is the inside surface from the fracture. You can see also that we didn't do we didn't transfer correctly the UV, so we're going to do this right now. Switch back to manual, and I'm going to copy the surface attributes, UV, and also first thing first, we need to create the UVs on those guys. So usually just a UV texture. So we need really, just going to do UV quick shade on the side. Obviously I do this before the maintenance, so it doesn't we don't like get deformed, but basically we want to have the UV to be deformed as well as the mountain, and not just reproject after it's been deformed, otherwise we might get some weird stuff happening. So we can see we don't see them. It is because the projection axis is not the right one, but if we just put a UV flatten afterwards, should be good, you can see. And so if I did that before the mountains, you can see it's I mean, it's alright, but like I feel it's cleaner to do it to project the UV and then deform it. So that's cool. And let's copy the same system over there. All right, not 2 times the UV. And also what you can do, so basically either you you want kind of like a really uniform way of cutting the planes, or what you can do as well is we can scatter some point as well on this line. So I basically remove all the iteration, and then I just, instead of 23, I just select 50. And we can see the difference. Basically, you can see like sometimes we'll have more cutting planes at some point, so we'll have more variation in terms of size difference in the pieces, and that's like one of the feature we're looking for with the Boolean. If I zoom out, you can see like those kind of pieces. So like we have some pretty big pieces, but we also have some smaller ones as well. All right, cool. So this is what we have with the scatter, and with just the more uniform way of distributing. You can see it's like it's small, looking like a deformed Voronoi. So I mean, like, you know, like there's just like sometimes we might want a middle ground. In this case, it's, to be honest, it's not that bad. I feel like it's already not too bad. But basically, so there's two things that we want to kind of separate by doing the fracturing. Basically, when you're fracturing something, the hard part to get is to get the edge displacement. So to get the overall silhouette of the shape. This is pretty hard to do, because like, yeah, by default, like when you do a Voronoi, that's basically the thing that you don't have. But like the inside surface there, then like we would be able to subdivide it later on and add some noise inside, but we can't really mess too much with the edge detail without like creating artifacts. So I feel like we should find the good middle ground of having something high res enough to get some nice details in the edge, but like something also that's still workable in terms of resolution, not something too heavy from the early stage of the fracturing. So I feel here in this example we might want to increase the resolution a bit. So I'm going to switch to 12, maybe 12 and 12. Something like that. Maybe 6. All right, and from now on, I'm basically going to bake as well. So I'm just going to copy paste the file cache we created. And we're going to do road second fracturing. So this part we can remove it. Well, we're going just to keep it as an example. So I'm just going to put some sticky notes around. This is really useful. So I'm going to do sample here, select and put like a drop box, network box, yeah, cool. Starting to kind of organize a bit our scene. So here we're going to do cutting plane, second fracturing. That's good. Also like give it colors, so feels about a bit more separated. Cool. Alright. So cool, let's try to save it to disk. See what we have. Okay, cool, exploded view. This is what we have. Let's see the details that we have. So I feel like it is a pretty good balance between too high res and not high res enough, just for at least the first phase, as we talked about. So yeah, I think it's doing what we want. So that's cool. Yeah, the thing we might want to check now is basically, you can see like the texture is not really following the geometry, so we might just need to do like a UV quick shade as well on the side. All right, and so it's because you can see like it's not on this, the newly created geometry is not on the same level as the rest. So I'm going to do like a UV transform. We can basically copy the one we created before. All right, but like instead of transforming the inside, we're going to transform inside too. And you can see here, yeah, around 7.5 is doing all right. So yeah, like now you can see the textures on the inside. So that's good. Good first step. So we have like, let's say this is the pieces that we want. We are happy about it. This is basically something that we can, you know, like we'll do a first test and then we'll see if we're happy with the shape of the pieces, and like this we can, the fact that it's being like totally procedural, like it will allow us to tweak the pieces as we go. Alright guys, now let's talk about fracturing. So I did like 3 different examples of the 3 main way to fracture stuff inside Houdini. The first one is Voronoi fracture. So it's pretty simple. You give 2 inputs, you just type Voronoi fracture, and you give the source geometry and you give some points. So basically the points are going to determine the look of the cell. So if I just look at basically, if I compare the shape of the cell with the source point, you can see that it's basically just each point I give will determine the shape of the cell, and like the point is the perfect center of each cell. So sometimes it can be like pretty uniform in terms of shape. So one way to remove this would be to remove the real life situation, and so now we would have a bit more organic patterns. You can also noise a bit the source. You can do a bunch of things, but like the main problem with Voronoi fracture now is that it's the edge details that we have is usually not is looking too low res. There's two main things about fracturing. There's like the interior details, so it's the amount of detail that we're going to add here, but the edge detail is basically the overall silhouette of each piece. So you can see here we have like some really sharp, non really organic shape, whereas, you know, like the one we used in to determine the area of work with the Booleans, it was like way more organic. We could we had more control on the way to. It's pretty hard to generate those edge details with the Boolean Fracture. That's why we can use it, but usually we use it more like as a sub-fracturing layer. So we do a fracturing with booleans, and then we can do another pass of sub-fracturing into small pieces with this technique. But like we use it less and less these days. The second way would be to generate counting planes. So that's the kind of the same system. I'm taking the input geometry, scattering point inside. I'm putting an attribute randomize of the n. So we're going to see different normals per point, and it's going to randomize the orientation of basically the grid that we're going to instance on the point. So we have this grid, we have a mountain, we copy 2 points. So that means like we have a lot of cutting planes, and basically it's going to calculate as like if the cutting planes were like a knife, and each time you see a cutting plane, you would cut your input geometry with it. So you can see right off the back we have something way more organic than the standards Voronoi. So like if I put them side by side, I increase a bit the size. You can see here is the Voronoi and here is the Boolean. So you can see the edge detail that we're talking about. So we have like way more organic shapes, and also we have more size variation in the pieces. So that's a good thing, obviously, but it also means that the Boolean would need more cleanup to also remove those very sharp looking pieces, and it can create some problems if we subfracture those and stuff like this. So it's definitely the new way of fracturing things now, is using is mainly Boolean based, because it gives like way more organic results. But it also implies that we need to do some other procedures on it to make it work in a bullet environment. And the main drawbacks with Boolean would be that it's heavier to calculate, but also it can generate some artifacts if you have like some non-manifold geometries, or if you basically if you do like a Boolean fracturing, and then on top of a Boolean fracturing and on top of a Boolean fracturing, at some points basically you will have the Boolean just erroring out. You will have some visible cutting planes. So it's way less stable than the Boolean fracture, but it gives much more organic result, as we talked about. The third way would be to use a node that has been introduced in Houdini 17, which is the RBD material fracture. So it's basically a digital asset with a different way of fracturing stuff, and we have different material type. So in our case, we can have a look at the concrete, and we're going to put an exploded view just under it. So you can see here in the concrete operation, it's basically, it looks like it's doing like a Voronoi, and it's more as what it's doing, but it's more like it is doing recursive Voronoi. So like you do a first pass of Voronoi like this, and then you re-Voronoi the results, and then you re-Voronoi. So this is what we call recursive Voronoi. And then you have some chipping operation, shaping, usually it's going to generate some transition pieces on the sides, and it's way longer to calculate. You can see here it's really fighting to get something out. All right, and then we have some pieces are kind of looking weird, looking a bit like charts. So it's a bit hard to control, to be honest. I found that I've been not using the concrete so much. Sometimes the wood is pretty good. Let's say if we have a box, and we're switching it to wood. You can see right off the bat, is doing his job pretty well. So we have some cool charts and everything. So the RVD module fracture is not something I would use. I've used a lot for the concrete, but sometimes it's something you can use for wood and for glass also, with some more radial sources, basically. So if I go to glass, basically you can see here it's going to generate radial fractures around a source point. Right, so in our case what we want is more something like a concrete, like asphalt. So as always, when you're working on an effect, you're trying to find references on the material you want to destroy. So like this is some few references of asphalt, broken asphalt. I just like lay out them in this little software called PureRef. It's pretty cool. So you can see that we have some like not really crazy charts. So it looks a bit like a Voronoi, but like we have also some size variation, and we have some cool edge detail. So I would say the thing that would look like the most would be this, but we feel like we're going a bit crazy here with just this technique of randomly copying cutting planes everywhere that are rotating around. We don't have enough control on the look that it's going to be. So that's why we're going to stay with the Boolean, but we're going to find a way to generate like more directed cutting planes. All right, so in order to do the fracturing that we want here, we're going to basically create two lines. One line that is going in the Z direction and is going to copy, orthogonal grid to this one. And we're going to create another line that is going on the X direction over there, and it's going to copy pretty long grid on the other side. So almost like kind of a grid system, but with cutting planes and Booleans. So you can see here the way I did it is I took the geometry, make a bound in oriented bounding box, and then I just created 2 points because you just need 2 points to make a line, and I just basically sampled those with the centroid and the B box operation. So then you have your line, and you have your 2 line basically, and then you can just resample it with the amount of grid that you want to instance, and there you go. Here, just don't forget to so here just a quick thing is to, on your fracturing Boolean, don't forget also to put the name to append. So that way it won't like recreate the job, but it would just put the name of the pieces after the actual name. So here you can see like I forgot to do it, so we were like having piece 0 and stuff like this. But now, after we rebake it, if I refresh, we can see that we have the road active that we created in the name, underscore piece 0, piece 162. It's pretty important, as I said, you know, because it will make sure that way that we have like really unique pieces, even if we have different stream of fracturing. We have our pieces ready to go, all fractured up. I just created a node called out unpack pieces. This is something that we're going to use later on. And the next step would be to do a node directed animation, procedural animation. And so yeah, the idea is to animate the pieces going upwards, and then at some point when they reach a certain amount, they will be activated, and then the gravity will take on and they will fall on the side. So yeah, let's get started. First thing I'm going to do, I'm going to create an assemble node, and I'm going to untick create name attribute because we already have those, but I'm going to click on create pack geometry. So that's it. Now we can see the textures disappear, and we have 163 packed primitives. So the points basically are the centroids of each piece. If I click on the add node and do delete geometry but keep the points, you can see basically the points are just the centroid, whereas as before, basically all the points were where the actual geometry was. So basically, it just says to Houdini, store this geometry and just display it as almost like as an instance. It's saved to disk in another space, and that way, basically the bullet solver will know that this is just one piece of geometry and not like each face, each primitive. Cool. All right. So basically now we have 163 different primitives and points. We're going to try to animate those. So to do that, basically the best way is always to play with the point cloud. So for example, let's say I'm creating a point that I can move around in the scene. I'm going to do an attribute transfer. Give it a black color for the source point cloud and a white color for the point we want to transfer the attribute from. So basically, if I put CD here so I don't transfer other attributes, I can play with the blend, and we can see that the color is transferred to those points. So that's cool. Now I'm going to play with the Y. So like I'm going to say p.y plus equals, so I'm going to add something, cd.r times channel float threshold. So if I click on the side here on this button, we have a slider, and basically we can multiply the amounts, and we're multiplying by the red data of the color. So that means basically when it's gray, it's going upwards a bit less. That's why we have this blending. Cool. So like let's just call this Y amount. Cool. So now if I do a transform pieces and I put the first input here and the second input we do transform pieces, we can see, wow, everything's broken. We can see we have a bit of the Y translation that we wanted, but like it's also really broken. And to fix that, basically what we're going to do, we're going to use a node called extract transform. So we're going to put the reference geometry, we're going to put the packed primitive, the target geometry, those points, and we're going to select piece attributes, because for now, by default, it's just making 1 point. And we're going to switch to point. All right, so now we still have the same amount of points as before, but like we have a new attribute called pivot. We also have the Orient, but like we're going to check the Orient is almost blank. We just have one in the latest. I'm going to talk about Orient later on, but like we can see pivot, we have some data. And so now basically we can see that it's not broken anymore. You can see like if I remove this, bam, it was broken, it's not broken anymore. All right, cool. So that's pretty cool. And now what we're going to do is we're going to store this attribute. So we're going to call it amount. So f for float amount equals cd.r. You will see why I'm storing this. So instead of using cd.r, now from now on I'm going to use amount. All right, that's cool. Now I'm going to start to animate a bit this guy. So basically here it's touching on this frame 1035. So I'm going to move the points on this guy over there. Cool. I'll left click for a keyframe, and then I'm going to animate it on the z-axis until it reaches, let's say, this position. That's cool. Alt click, and then on the animation editor, and if you don't have it, you just need to click on plus and you do animation editor. All right, and then in the function, basically, so what we have currently is a Bezier. So that means like it fades in and fade out, but like what we want is a linear. So that means like we don't have any fade in or fade out. That's cool. So this thing is animated. And here we're going to play with the blend as well. So let's start with something pretty slow. Like we can start at 0 basically. And here, a few frames later, we can go back to something around 8, maybe a bit less. 5. Sounds better, right? Bam. Alright, so we can also, yeah, we can change a bit the timing to make it follow more the camera over there. That's cool. All right, nice. And now here on the Y amount, I'm going to multiply it by another float called animation. It's pretty handy to do this. So basically, the animation will be like a 0 to 1 float that we can easily animate, and then it will be multiplied by a threshold. So that means we can just change the overall amount without changing the animation keyframe. So that's cool. So I guess on the first frame we can be a bit more gentle. And pretty quickly we can go back to 1. Same thing, switch to linear. All right, that's cool. Nice. So now what we're going to do, we're going to create a solver, and we're going to do a max solver basically. So the reason for that is we want to store the amount, because for now, basically you can see when those guys are after the point, they are not white anymore, basically. So like this is the amount attribute is being, you know, like going back to 0. So we don't really want that. We want to store the maximum amount it has got on the full frame range. So in order to do that, we're going to create an attribute triangle, connect the first input here, and the previous frame on the second input. We're going to create an output node, and we're going to call it max solver. And we're going to call the amount attribute equals max amount in point. We're going to call for the previous frame point 1 amount ptnum, because we're sourcing on the same point number. Cool. So now we got this. Let's see what we have. So we can see the color is still moving, but I'm not really visualizing this the amount attributes. So to visualize it, I can put like a color node, ram from attributes, and put it amount. And you can see now, basically, it stays to the maximum amount it ever has. Cool. That's pretty cool, because we're going to store this maximum amount. So in order to do that, I'm going to do a time shift, call $rf end for the end of the end of the frame range. So like now we're not in time dependent mode. We're just like, this is just a static frame, right? And we're going to store this data. So we're going to call f max amount equals amount. Cool. And then we're going to use an attribute copy. Remove match p attributes, and we're going to call it max amount. We don't need to match it because it's the same point count. So then we're good. We're going to use it later. We'll go back later on that and why we're actually doing this. Cool. All right. So now this is what we have. So the first thing that we want to change now is the orientation of the pieces. Basically, now it doesn't feel really organic, right? Because everything is going upward, but like in the same way, in the same rotation. So yeah, we're going to tweak that. And to do that, we're going to play with an attribute called Orient. So here we can call it orientation. And so the Orient attribute is created by default with when we did the extract transform stuff. So we can have a look at it. And you can see here it's a vector 4. So we have 4 floats, all zeros except the last one, which is a 1. Cool. And now, basically what we want to do is we're going to create another, so like those vector 4 are called quaternions. And basically we're going to create another quaternions to multiply it and tweak it. So basically, I'm going to call our first vector 4 pitch, let's say. And we're going to use the quaternion function. And we're going to basically give it a vector. So like basically it's on which axis we're going to rotate the pieces. So for the pitch, we're going to put 1, 0, 0. Cool. And we're going to multiply it by channel float pitch. That's cool. All right, so you can see here, nothing is happening. That's normal. We can tweak it, nothing's happening. It's because, so now we want to multiply this quaternion by, we want to multiply our Orient by this quaternion. So we're going to call the Orient attribute, so P Orient, Q multiply. So we're going to multiply two quaternion, and we're going to put back the Orient, and in the second input the pitch. And now we can see something is happening, right? Can you see that? Okay, cool. So like, what did we do? The x-axis is this axis, right? So actually we are rotating stuff along the x-axis. Okay, pretty cool, pretty cool. So the thing is, even if it makes sense to have some in the air like this, well, we don't really want to have any rotation when basically it's not applied yet. So we're going to call another attribute. So we're going to create a float channel rotation, and we're going to make it let's make it the color for now. cd.r. Cool. And so now basically here, when we multiply by the pitch, we're also going to multiply by this float rotation. And you can see here that it's multiplying by the color, right? So that means like all those guys are not rotated yet. All right, pretty cool. So yeah, now let's try to make those dynamic, right? Because like obviously we don't want to keep the pieces in the air. We want like once they're like a certain point, to make them dynamic and to have the gravity affect those, and so like to make those fall down and collide with the collisions and stuff like this. So we're going to create a dot network, and we're going to dive in, rigid body solver, RBD packed object. We're going to look for the first convex geometry. We're going to generate the velocity from point velocity, reduce the bounce. And so yeah, that's the last thing we want to do. So like we have some stuff moving, but we didn't really have any velocity, even though they are moving. So we're going to put a trails up, and we're going to compute velocity. And you will see it will be automatically applied to those guys. We can see the velocity values changing. Cool, all right. So now we're going to put a ground plane as well. So it's an infinite ground plane, right? And we're going to put the position to -1. So I have something like this, and then if I hit play, what do we have? Well, we have nothing. Nothing is working because like we didn't put any forces. So now we're going to put a gravity to see basically what is dynamic, what's not. All right, so cool. Everything is falling now. So you can see already we have some like pretty decent shapes. Looks a bit like concrete, so full fracturing is all good, and we might just change it later for like if we want to change the amount of pieces or something like this, but it's more like some odd direct stuff. I'm going to call this main pieces. Cool. And basically now we're going to try to make everything unactive. So I'm going to switch create active object to create animated static objects. Fair enough. It should work by default. Cool, so now we do have the animation. Awesome. Now I'm going to dive right in and create a subsolver. Put it in the pre-solve. So subsolver can be a bit confusing at first. Basically what you guys want to do is just like play with the doping ports, because we're not going to play either with the impact of the feedbacks or the relationship geometries. So for now it's just this. It's basically the pieces. We're going to put an output and we're going to do stuff in between. So in between I'm going to put an attribute triangle, and in this attribute triangle I'm going to check some stuff basically. So I'm going to say if amount greater than activation threshold, I'm going to say I active equals 1 and I animated equals 0. So those two are like rigid bodies bullet attributes. Active means like it won't be active animated anymore. Animated is just to make sure that we don't have any weird stuff going on. So I'm just going to call this activate pieces. See, cool. And so here I'm just going to click on this, and the threshold, let's make it 0.1. So now what do we have? We have nothing. Why do we have nothing? Well, it's because if I go to the geometry, I look for amount, everything is set to 0. And it's because I didn't copy the amount from the point cloud to the actual pack geometry. So here I'm going to click on attribute to copy, and I'm going to put amounts. And if I look for amounts, I can see I have some 0 to 1, mostly 0. Alright, cool. That's because I was not looking at the right frame, but yeah, you can see here some amount stuff. Cool. And also, it won't work neither now, because I need to overwrite each frame this attribute. So it basically is going to say copy by name on each frame. So now we have something going on, right? Let's have a look in the camera view. You can see that they are falling. They are following the animation at first, and then at some point they are just falling down, which is cool. We have our main simulation. The setup is working, so now we just need to like do some tweaks to make it look good, basically. The first thing we can change basically is to tweak the orientation amounts that we give it. So I'm going to like emphasize a bit the pitch that we created. With something a bit more extreme, like at 1. You can see it's pretty pretty fast to calculate, so like we can do some iterations quite easily on it, so that's cool. All right. All right. So that's cool. And now we're also going to play with another orientation. Basically, I want to have like an overall more spheric shape. So like I want the pieces on the left side to orient in this direction, and the pieces on the right side to orient in the opposite direction over there. So in order to do that, we will need a vector, because like the orient, like the orientation of the piece depends on whether it's on the left side or the right side. So what we can do for that, we have like these points basically that generates the timing of our flipping stones. And I'm just going to put a null plug in here, and I'm going to create this vector of around here. I'm going to plug it in the second input of the attribute triangle, and I'm going to create a normal attribute. So I'm going to do at n equals 0.1 p position 0, because it's the 0.0 that we're looking for, minus p. Basically, if we look at the normal, now we have the vectors pointing to this guy, right? Cool. So that will help us to determine like on which side we want to orient the other one. Cool. So for the name of this one, we're going to go with let's call it roll. Right? Yeah, roll sounds good. So Victor 4 rolls equals quaternion. And so here we're going to give a different vector. So like, let's try 0, 1, 0 times n and times channel float roll. That's cool. So now we created the quaternion, and same thing over there. We're going to Q multiply the orient attribute that we have by this new vector for this new quaternion that we just created. Alright. So now if I just go back to transform pieces here and I just play around in roll, I think that's not basically the right vector that we're aiming for. So I'm just going to try on the other side. So I think that's kind of the one, yeah. All right, that's cool. Basically now I'm going to, so like the normal was good for just like the visualization of it, but I'm going to create a vector called roll side, and this one is going to be a custom vector 0, 0, and we're going to look at the nx value. Cool. Nx. And instead of multiplying by the normal, we're going to multiply it by the roll side. And bam. Now we got like this cool shape that we wanted. So of course now we need to multiply it by our float, the rotation, which is going to just constrain it to not rotate everywhere, but just on the part that is supposed to be activated. All right, so that's cool. Let's try it out. How does it look? All right. And now I've got a feeling basically like the pieces are getting activated a bit early. And so the thing is, the activation threshold. So I can try to play with that number for sure. Let's try it out. So now I just put 0.5. So we can see that now we're keeping more of the animation. But the thing is, basically, we're going to have some artifacts. Those guys, basically, you can see, they will never make it to the 0.5 threshold, so they're going to be stuck in the air, and basically that's not what we want. So in order to fix that, remember, just before I created this, the max amount, and so here we're going to use it again on the subsolver. So yeah, the idea for this one, I'm going to try to explain it the best I can, but it's basically, I'm just going to put it back to 0.1 so we don't have those guys stuck in the air. But I'm going to say, basically, if you're at 0.1, but you're only less than, let's say, 50% or 70% of your max amount, don't activate yet, and basically check that you're near your max amount before you're getting activated. So let's try it out. Here on this line, we're going to put the and symbols, so like in the condition of the if. So the, forget every time where it is on my keyboard. All right, and so like this double and here is going to say you need to follow the two things to basically get activated. You know, like either you play with and, either you play with or. So the or is this one. But in our case, we're going to play with the and we're going to use the same attribute and amount higher than max amount. So let me check how I spelled that. So like this is one of the useful cases of having two windows that, you know, like you don't have to going back, and you can just basically check on the same view. Max amount, that's cool. So I'm going to copy and paste this. Oh, just going to put the F at. And then I'm going to create a channel float. And I'm going to explain just a bit later. Max amount threshold. And we have, and there, where's that? Max amount. All right, I think it was just because I was, yeah, I think the error is gone now. Cool. So now we're going to do a test with this, and we're going to set it to 60%. So the idea here is we're going to activate the pieces that are that have like this 0.1 amount threshold, but we're going to basically keep them on the static animated, just on the procedural animation, if they are this amount, the amount attributes is lower than the 60% of the maximum that they will have on the whole frame range. So let's see how it looks basically. Cool. So let's see if we have the max amount attribute, and we don't have it. That's why basically it basically looks the same. So I'm going to copy as well max amount here. Cool. And now let's check it again. Cool. So now we can see basically we have a lot more of the procedural animation. You can see here we're keeping this translation. Well, this orientation, sorry. So now we're keeping this, and we don't have any of those like residual stuff that are stuck in the air, which is a good thing. Cool. All right, nice. So I feel like now the system is working. It's looking way better than before. So we're in a good place. I'm going to talk a little bit about Bullet and just the system it's working and how basically it's working. So Bullet is going to work with convex geometry. So what is a convex geometry? The best example to do that would be like, I'm going to like just a standard geometry, so like a pig head, and I'm going to create a convex hole. And so this is Houdini's vision of what is convex in this geometry. So basically, all the geometry that are like pointing outwards are convex, and all the geometry pointing inwards are called concave. So basically, if we just give it a pig head in an RBD simulation, like, let's just try it out. RBD bullets. I need to create pack geometry. Grid. Basically, Bullet is going to see this. It's going to see this guy instead of this guy. The reason why it's doing this is because it's like way faster to calculate that way. And so we have like several options on our RBD packed objects, and we're going to have a look at those basically. So if I click on this, remove display geometry, and click on this guy, show guided geometry, bam. So like this is basically what Bullet is seeing of our geometry. So it's pretty important to know this, because like basically the collision is not going to be this guy, it's going to be this. So you can see that at some point we might have some like intersecting geometry and stuff like this. So in order to fix this, what we're going to do is we're going to create a convex decomposition. So basically we're going to almost like fracture this in small pieces, in small convex pieces. And let me show you what I mean. Let's get pig head over there. So if we wanted to have a more defined representation of pig head, we could do, there's basically two different workflows. The old-fashioned workflow would be to Voronoi fracture it. Sorry, over there. And then we're going to put for each connected pieces, and we're going to put our convex hull over there. So you can see over there, as we're the more we fracture the pighead, the more we can have representations. Basically, it's going to say each piece, so each of those guys, I'm going to apply a different convex hull. All right, and so, but the thing is, if we do here an assemble node, and we just run the sim, basically we're going to see it's fractured, so that's not what we want, right? So basically the trick here is to copy the name. So like we will need to give it a name before. So like here I'm going to remove create name, copy and paste this assemble node, create name attributes, and remove create pack geometry. And so now if we look at the name, oh yeah, and we need to create the name basically before this fracturing stuff. So basically now we have we can see, oh, it's still the same. All right, so like here it's going to create the names no matter what. So what we can do is just like we're going to override the name. I think it's a better option. Name equals pighead. So if we do this, create name attribute. Why is it not working? Alright, it was just like not refreshing enough, but yeah, it is working. So we can see now, basically we have like a better collision of the pighead. So it doesn't make much sense to like have this precise representation for this case for just like a falling piece. But like if it's colliding with, you know, like smaller spheres, let's say, and it will go like under the ears, basically it would make sense to do like this kind of representation. So that was kind of the old workflow, and so then, you know, like we need to call the non-fracture geometry and call it back. So it was kind of a bit annoying to work like this. So now basically, since I think Houdini 17, we have a new node called Convex Decomposition. And so here it's going to just keep the same name that we had, and just by changing the max concavity, yeah. We're going to do the exact same workflow. If we have a look inside, okay, we can't, but it's basically just like a Vono with some convex in for each stuff. So basically, this is what we need to fetch the sim. So the thing is, with this workflow, we can't really use this geometry. We don't want to use this geometry for the final render. This is just going to be a proxy. And then we're going to export the result of our sim. So it will be a point cloud with Orient scale and transformation data. And we're going to then just move the high-res geometry with the sim. So it might sound a bit confusing right now, but like it will make it will make much more sense afterwards. Cool, so I'm going to do a bit of cleanup over there. And call it procedural animation. Cool. Let's give it a cool blue color. All right. So I'm basically what is going to change here. So I'm just going to do a bit of space between the fracturing and the procedural animation stuff. And I'm going to create basically the convex decompose stuff. So creating this convex decomposition node, I'm going to copy and paste our file cache, and I'm going to call it roads convex decompose. And I'm going to plug it in. I'm going to do like a switch. All right, and let's see what we have. So you can see here, it doesn't look that much different so from what we saw earlier on the bullet. So we will need to reduce the macro connectivity. The best way would be, I'm going to just keep one of the piece. So I'm going to click on this little arrow over there, go to primitive 9 on the keyboard, select by name, and I'm going to select one of the piece. So let's select, for example, let's say this one. Delete non-selected. And basically, this is what we have. So basically, Bullet is going to see just the gray stuff. So our goal is to make it look more or less like the original piece, right? So I'm going to basically tweak this max concavity stuff. So like this. So basically, we can see that like the more I reduce this, the closer it gets from the source geometry. So I'm going to go like across over there. Sounds about right. We don't need this to be like 100% accurate, right? Just it needs to be more or less good. All right, and so now basically I'm going to go there, signature manual, bypass this. So we will apply this on all the pieces, and I'm going to go save to disk. Cool. So let's see, what do we have now? All right, so we can see now we have like much better representation that we had before. So let's go back. Let's put a backdrop over there. Cool, pink. Let's go back and let's see what we have for what we see for bullets. So you can see it's pretty much the same, right? It looks pretty much like what we used to have. And the reason why, it's because we will need to create convex hull per set of connected pieces. All right. And also we will need to basically giving the right geometry to bullet. Let's see what the difference makes. Bam, you can see just by doing this, we have a much better representation of the overall shapes of the geometry. That's pretty cool. We have also the basically the point of this is to make sure that we don't have geometry that are intersecting at first, and that might just create, you know, like kind of explosive situation. So sometimes it can be like a bit heavy to display this. So I'm just going to turn it back to display geometry. So we can see like all the normals are broken and stuff, but it doesn't really matter. So now let's try to do the workflow we're talking about, and basically transform our IRS geometry with the data from the sim, and also like I'm going to talk about the efficient way of caching an RBD simulations in Houdini. So here in sub level, I'm going to create a DOP imports, and I'm going to create points to represent objects. I'm going to give it RB2Sim in the dot network, and pretty interesting stuff. We have object mask. So in the event, we have several RBD packed objects, and basically we're going to select which one we want to extract from the sim. So here I'm going to put star main PC star. And what do we see here? Basically it's the same that we have there. A point cloud, that's just to represent the geometry, right? Cool. So now let's try to get our IRS geometry back. So I'm going to put an object merge. And remember this null I created? This was basically just to be picked up afterwards. So I'm picking up the unpacked geometry. And I'm going to create a new transform pieces. And voila. Now we have, you can see the high-res geometry being transformed by the RBD-Sim. Also, the really good thing about it is that if you think about it, we're only baking points. So that means like the caches will be really light. So now I'm going to create a file cache for our RBD-Sim. I like to create those switch so I can basically each time switch between caches and like dynamic simulations. So road, let's call it road main RBD simulation. So in this case, we need to bake the frame range, and we also need to put $F. In my case, I'm going to put $F4, and so that we don't override each time the frame, because basically if we don't put this, like frame 1000 will bake, and then frame 1001 will override frame 1000 and go on until the end of the frame range. So like we need to store those frames into different file each time. Cool, so let's try it out. Save to disk. You can see for now it's like really light, and that's kind of what I like to, and I think we when we were like prototyping effect, we would try the most as much as possible to just keep it pretty light at first, and then working per layer, and again, basically not starting with a huge amount of geometry, because like each time iteration will take much time to operate. So cool. So like the system now is working. We might need to do a few tweaks. I feel like they might go a bit crazy high, so we can reduce that with the Y amount. I think the orientation is fine though. I'm going to make sure alright, so we inherit the velocity from the points. Alright. Cool. What we can do now as well, we can break that up. So we're going to create an attribute VOP, and we're going to call it large noise. and I'm going to bind export it as a float, and I'm going to call it big noise, and just put it in CD as well so I can easily visualize it. And here, right click, vex, create input parameters. So we just put everything, we just promote everything on the node instead of having to dive back in each time. I'm going to switch it to sparse convolution noise. I kind of like it. It's a bit more rough. I'm going to play with basically a low frequency noise. And I'm going to create another one. This one going to be the small one. I'll do a clamp as well. Clamp to, I don't know, 3. Alright. And this one I'm going to play in like a higher frequency. Okay, cool. So now let's try to alright, here, so the mistake we made, it was we need to use the mount instead of CT. So that's still working. And basically here what we can do is we're going to multiply it by the small noise. Yeah, so we need to pick that out as well, small noise. And we're going to fit this, fit 0, 1. And we're going to put 0.3 and 1, maybe a bit more, 0.5. Yeah, so like it's not totally perfect. You can see if I remove this, here it's perfect, here it's a bit more broken up. Can increase this and pitch this a bit more. And I'm also going to do it on the height. And this one, maybe we're going to use the big noise. Alright, so now it's a bit more broken up, basically. It's cool, let's see how that looks. Damn. Alright, maybe now we can compensate by increase a bit the amount. Alright, so now we got like cool stuff, I feel. Yep. All right. I'm happy with that. Cool. What else can we do? So the next thing, because so now we're just only working with this layer, but basically we can see here, for example, we will need to put the sidewalk as collider as well, and like the non-active part as well. So let's do that right now. I'm going to remove this pig head stuff, and here we add, remember, the non-active array. So let's put that up, and here let's create a new non-active collider. All right, going to object merge this so we don't have bunch of lines everywhere. Cool. And remember, we're going to use basically the same system as here. The convex decomposition workflow. Because like let's try if we do like a convex all of the whole thing. Basically we have this. So like all the inside gaps will be recovered. So that's basically not that what we want at all. So let's try it out. So that looks alright. That's cool. We're going to rename this. So we're going to say road an active convex decompose. Right. Save to disk. I might just change the folder where we're baking the sim. I can put all the simulation in the simulation folder, so it's a bit more organized. All right, have this here. That's pretty cool. I'm going to say in non-active packed collider. That's cool. I'm going to assemble, remove create name attribute, create pack geometry, and the name we're going to give it a custom one. Name equals an active road collider. Cool, let's try it out now. Let's do another RBD packed objects. I'm just going to drag and drop. An active road. Going to remove this, we don't need. The override attributes, sub. And I'm going to drag and drop this, and we have also like the create convex decomposition per set of connected primitive. Cool. Let's see how that looks like. Bam. So basically now we have the good collision with the rest of the ground, which is a bit more accurate than what we used to have before. All right. Cool. Even though it's in this case it's working pretty well, I kind of find that it's pretty often faster when we give several collision pieces rather than a big one. So let's just start the opposite way. We're going to create name attributes, and here in name I'm going to switch it to point, and I'm going to say plus s name. So we can see we'll give 352 fragments, and basically that will allow us not to use the create the convex all per set of connected primitive. And so like we can see basically the result is going to be the same, but it's going to be basically the solver will like it better that way in most cases. All right, cool. So next step would be to add the sidewalk, so like we can import it as well. So I'm just going to clean that up a bit. Let's put that in purple, and I'm just going to call this guy out, sidewalk. I'm going to do the same thing over there. Let's duplicate everything and just change the input. Sidewalk collider, giving the brand stuff. Let's create some name. Alright, so we can see basically by default it's, in our case, it's just like some pretty basic geometry, so it's pretty easy to calculate, but just that way we don't have to think about it too much if, you know, like they change the geometry in an environment. So basically it will stay procedural. All right, an active road, sidewalk. Cool, and effects work. And here we go. All right, let's see how they look with all the side colliders. All right, looks pretty good. We have all the collision working, so we don't see enough, like much interaction with the sidewalk anyway for now, but maybe that will change later on. Let's close that up, and so I'm just going to put again small stuff here to keep everything organized. Import sim. Sim. All right, cool. So now what I will what can we change? What can we improve with this? Basically, so we can see the so the size of the pieces is pretty uniform. We have a bit of variation, right? For example, look, those really small pieces that can get distracting, so we might put like a pop speed limit and stuff like this. What else can we change? So yeah, basically the size is a bit uniform, and also it feels a bit empty, so like we would need basically the roads are never just one layer, you know, like they're composed of multiple layer of asphalt, and maybe like we'll have dirt under it. So let's find a way to maybe put smaller pieces underneath that. To do that, I'm going to show an example with instance geometry and how we can basically generate pretty efficient way to generate a lot of pieces that we can reuse a lot of time for underneath surfaces. because usually, yeah, we cannot really touch the geometry that is visible, like the outside geometry, because like they might come from another department, usually environment or assets. But like if we want, we can add additional geometry underneath it. All right, so let's add those underneath geometry that we're talking about. So I'm going to create a grid, and let's do it 7 by 7. Grid 10 by 10 is all right. And we're going to create textures, so we would have those for later. All right. Do we have? So we have UVs now. I'm going to do a poly extrude, and yeah, poly extrude over there. Distance minus 0.5. Output back. So now it's like closed geometry. I'm going to do a reverse. So then now the normals are on the right side. And we're going to generate some pieces. So let's call, yeah. Let's do scatter node. Let's do an attribute randomize. So here we're going to generate cutting planes, like one of the example that we saw earlier. So I'm just going to recreate this pretty quickly. That's not really long to do. Let's put it inside sphere. I'm just going to keep though the grids with the resolution stuff that we saw. Reach points. Boolean Fracture. All right. And let's copy the UV as well. Let's put an exploded view. Bam. All right, cool. So now we have some like pretty high-res geometry. It's not really uniform, which is good. The only thing now is it's going to be a bit heavy if we have that many different instances. So now we have like 62 different instances, and we have like a lot of different small pieces. So the idea, as we don't really see them from the start, we can basically get away by removing all the small ones and just keep the mid-size one. Cool. So now let's first let's first check that we have UV on the inside surfaces. So UV quick shade. If I do UV transform on the inside group, oh wait, because we don't have any, because we forgot to put a UV node, UV texture. On the grid. So now if I go back here, UV quick shade, I have some UV, and we copy why is it on the points now? UV, no. Why do we have this? Oh yeah, it's because we had some UV on the points that we inherited from this geometry. So now basically I'm just going to remove all those attributes. Now we do have the UV on the vertices from those guys, and then now we have some UVs on the inside surfaces. Cool. So let's make it roughly uniform. Cool. And basically, so now what we're going to do is we're going to calculate the area of each piece and basically split the small ones by a certain amount. So in order to do that, we're going to use the measure sub. Put the measure by area, and we can see we do now have an area attribute in the primitive. Thing is, now the area is working only per primitive. So now we will need to get the sum of all the primitive per pieces. So in order to do that, I'm going to create an attribute promote. Our primitive from primitive. And there's like a cool new feature, I think it was like in Houdini 17 maybe or something like this, called piece attribute. And basically what's going to do is just going to promote the attributes per piece. So it's because before we were supposed to do like a for each and promote them in a different way, but just by clicking this, it will get the result that we want. If we put to sum, basically now all of those area attributes will get added per piece. So now if I do a split, I put area greater than, and I just click on this wheel over there, and I create a float channel, threshold, cool. Copy parameter and paste relative reference. Here we'll have the big pieces, and here the small pieces. And you can see by just turning up a bit the threshold, we can see we have a lot of the small pieces. And that's really cool because now we went from having 62 different pieces to having 22 different ones. Basically, we can check. We got rid of all the small one and just kept the mid-size ones. So yeah, that's pretty awesome. Let's just bake as well, so we don't have to recalculate each time the fracturing of those. So I'm just going to copy my file cache, and I'm going to say under pieces fracturing, save to disk. So now that we do have those big pieces, basically what the plan is to copy those. So we're going to do like a copy and transform. Let's put that like that. So it's a bit big, so I'm just going to transform them down. Like at 0.2. And then I'm just going to put it on the side of the road. I'm going to copy and transform. And I'm going to create more. So maybe 5. Yeah, that much pretty good. So yeah, that's cool. And then we're going to create another copy. Oh yeah, we might just want to move them as well a bit over there. Because like all the pieces are going to be generated from here basically. Alright, that's cool. And then we're going to create another copy and transform. And yeah, we're going to have it, I don't know, more than that, 30 times. Bam. So now we can see basically we have like a lot of geometry. Like we have 1 million, 2 million geometry by just basically having 22 pieces. So yeah, that's pretty cool. Now what we're going to do basically is we're going to store the original name. So yeah, let's first do this. We have here the pieces, right? Centered at the right scale. In under pieces. HQ. We're going to create a name. Create name. And so as we already have a name from here that has been already generated, we're going to just add something before this name, like under pieces underscore plus name, and in primitive. So now we can see we have those names. Cool, and we're going to store this name in the Orient name, in an Orient name attribute, and you will see why in a bit. Orient name, or yeah, maybe name Orient for name original, right? That's fair enough. Let's put an ensemble, remove create name attribute, create pack geometry, and now we have this. All right. So what we're going to do is we're going to try to re-instance those guys here, and yeah, I'm going to explain it a bit later why we'll do that, but usually it's a better workflow to just extract those information. So I'm going to create an attribute triangle over there. I'm going to call it gate transforms. And here I'm going to create a matrix for packed full attributes. It's going to be the prim interesting attributes 0, and we're going to look for packed full transform. And we're going to look for PT num. So basically, you don't see those. The only way you can see them is by going to the intrinsic tab in the primitive. And you can see we'll have this packed full transform. And so basically now we're going to calculate what do we need basically to go from here to each of those points. So I'm going to create an attribute So like now that we have basically this matrix, we're going to convert the matrix into Orient, scale, and transform attribute. So let's create an attribute VOP here, and we're going to create transform. We're going to call it transform matrices to attributes. All right. So now I'm going to create a bind, and I'm going to look for the packed full attribute that we just created. I think it was like this, right? Packed full, and it's a 16 float matrix, 4x4, and I'm going to create an extract transform node. Packed full, and we're going to plug into XForm. So now we can see basically it's going to translate those as the standard transform, rotation, scale stuff. But to get the rotation, we will need to convert degrees to radians, and then we're going to convert the radians to a quaternion, and then we can bind export it to the Orient quaternion over there. Cool. So now we exported the Orient, we're going also to export the scale. Right, bind export scale and free float vector. That's cool. And transform, we're not going to use it for now. You'll see why. Cool, so now that I have those information, I can put an add, delete geometry, and keep the point. So basically, this is all the different pieces. So now we have, basically we have 3,000 pieces, but only 22 different instances, all right? So now let's try, we're going to do a for each name primitive here, and we're going to snap each piece to the center of the world. So in order to do that, we're going to do minus $CEX minus $CEY minus $CEZ. Cool. So now basically each piece is snapped at the center of the world. We're doing all this so basically at render time, and even like on the next step, we could have like thousands of different pieces and be able to just instance those guys at render time. In order to do that, we will need to snap the source geometry to the center of the world. So now how do we copy those into the points? Basically, we can try to do the standard copy to points, right? Let's try it out. And maybe this time let's put pack and instance. So that seems to work all right. And the only problem basically is that we're copying 22 instances each time. So we will need to switch per instance, right? So only copy the under piece 0 where it's the under piece 0, the under piece 1 where it's the under piece 1, and stuff like this, right? So what about we do for each name prim, so we should indicate 2 points. We'll have this over there. So we can check that we're looping 22 times, so the amount of piece that we have. That's cool. Let's select this and create a metadata import node. And we're going to duplicate this and just fetch the input. All right, nice. So basically now we're going to do a blast and we're going to remove everything that is not the correct piece to copy. So in the blast, I'm going to click on the wheel, and add sphere input. I'm going to drag and drop this. And that way, basically, I'll be able to say name Auric equals detail s -1, because we're looking at this, the metadata import, and we're going to call for value. Guess from points, it's going to be points, delete non-selected. So we can see by default, like, we don't have anything. And that is because the name Auric is a primitive attribute. So here I'm going to attribute promote name Auric from primitive to points. Still not working. Why is that? Do we have the name Auric over there? No, we don't. Yeah, so we don't have name Auric here. But basically we can do just name equals name Auric. Now detail as value. Oh, and yeah, we might need to put those little guy for string. I don't really know how you call those, but right, why is it not working? Let me check. So we got those, name Auric. No, it's going to be name Auric. I don't know why it's changed to name. Okay, cool. So now we have some geometry, and bam. Basically, this is what we had before. Cool. So now basically we know that we can instance those guys back into the geometry. We know it. So I'm just going to put here another null in under piece instances. So that's what we're going to use at render time. All right, that's pretty cool. So now we're just going to remove, I'm going to remove this packed full stuff. And yeah, cool. So now we have the name. Here we can, let's promote name Auric as well. And we're going to promote it to points. All right, so now we have both of them, and basically for bullet, we're going to tell him that those 3,000 different pieces are different, have unique name basically. So in order to do that, we're going to do another wrangle unique names, and we're going to say under piece. We're going to say as name plus underscore plus ITOA PT num. So ITOA is going to transform an integer to a string. And basically, we can see now that we have unique name attributes. So like now, Bullet will recognize that those guys are totally different. So that's cool. Let's clean that up a bit. So we have under pieces fracturing. Over there. We have under pieces split by area. Here, here, under pieces placement, under pieces instance prep. Let's call it like this. Cool. Here, under pieces, bullet prep. Cool. So now what we can also do that we didn't do is we can do another copy and transform. And we can slide it down a bit to create more layers to this guy. So we can do like for, so you can see like if I do for example 10 times with this kind of workflow, and that's basically why I reinstance them, because like you can see here my viewport is getting a bit laggy, but then when I just recopy to point them, basically Houdini is going to understand that, well, it will be more efficient in terms of memory. Cool. So yeah, let's just for now let's put maybe 3. That'd be enough. Cool. In 100 pieces. Okay. So we're not going to put them as in the same stream as the rest. We're going to create another one, and I'm just going to create a null over there in packs outer road, and I'm going to basically duplicate what we just created here. Cool. And just remove basically the assemble that we already have. Cool. So we can see basically now we have the same system, and I'm just going to do further adjustments. So just on the side, just to double check, I'm going to put the 2 like this. All right, so I think it will look cool. It's just for now. Let's just time shift our animation per one frame, so we don't have all this all this geometry just like getting interpenetrating. And I'm also just going to maybe reduce the maximum radius of the active area that we'll have. Maybe that was enough, then maybe we don't need this time shift stuff. Yeah, that look alright. Cool, and here we're going to create, so like in under pieces packed animated. Cool, and now if we dive back over there, and we will create a new one. Same domain pieces, but just this one is going to be called under pieces. And let's do it by sub, and we're going to drag and drop this. Cool, let's see, what do we have now? So now it's going to be, I think, a bit longer, that's for sure, because we have way more pieces than we had before. But it shouldn't be that long, I think, so. Cool, so basically now we can see we have like a much more fuller road. And I think, yeah, I think it's working pretty nicely. Yeah, I think that's cool. So basically, this technique is really like memory efficient, because instead of having to spend a lot of time in like regenerate a lot of different pieces, we are saving time in fracturing. We're saving time. We'll save time at render time as well, and we'll save time in the sim, because Bullet will understand that those guys are just the same pieces. So you can see basically we have done the simulation in less than 2 minutes. So it is pretty efficient. All right, that's cool. Pretty happy about it. And now I'm just going to also import the on the road point cloud. Import main road imports under pieces. And by just changing the object mask to this, now we have the outer road pieces, and here the under pieces. And if I just want to visualize here, I can go in under piece. All right, so like this is everything that we have underneath it, and this is what we have on the outside. If I do a merge, basically that's what we have. All right, that's pretty cool. Let's save that to disk.